Welcome back to our session on measuring information transfer in complex systems. In this short video, we're going to look at the transfer entropy measure that we've introduced in the previous short videos, and we're going to look at how to use it in practice. We're going to look at how to set its parameters, and I'm going to show you how to set those, in particular, when you're measuring transfer entropy using the JIDT software. Our first consideration here is how to set the target embedding. That is, how to set the parameters to examine the context of the past of the target. We have similar concerns in doing so as we did for the active information storage in our previous session. And indeed, we can include an embedding delay here, which I didn't show you on the previous formulas that we looked at. We could embed every thousandth value. We could skip values. Instead of having consecutive k values, we could have every second value or every third value, and that's the tau parameter here, the embedding delay. So we have an embedding dimension k and an embedding delay on our past embedded state here. So we have similar concerns in setting that as we did for the active information storage. In particular, what we want to do here is to minimize stored information from being counted as information transfer. And so that means we're going to try and maximize the information storage that we can reliably detect from the past. So we're going to use a bias-corrected active information storage, all the Rugvitz criteria, all the non-uniform embedding criteria that we discussed in our previous session on information storage. The first two options here, the maximum bias-corrected AIS, all the Rugvitz criteria, are implemented and available in JIDT. There are a couple of caveats to consider here in setting this embedding on the target. What we have to make sure that we're doing is embedding the target first before trying to embed the source, and we're not embedding the source and the target at the same time. We're embedding the target first so we can properly interpret our result as modeling information transfer. If we don't do that, then we have not given priority to the information storage first. As we've been discussing, from our perspective of information processing, we prioritize measuring the information storage first, and then the transfer as a second step after that in our modeling of the dynamics. So we must embed the target first. So we properly measure information storage first and then measure transfer. That's very important. Also, we must understand that once we've done that though, additional target pass values could have been missed here, which could add synergistic information with the source. So it's possible you could come back later after you've embedded, you could embed the target first, then think about the source as we'll do in the next few slides, and you could have a last step to come back and look at more potential values from the target to condition on as well. That's not something we normally do, but it's just something that we should bear in mind as a possibility. So let's have a look at how to set these target embedding parameters in JIDT when we measure the transfer entropy. Let's go across and have a look at using the KSG estimator, and we're going to look in particular at the auto embed method property, which provides us the options for target embedding here. Okay, so I've got the KSG estimator here and the transfer entropy auto analyzer. The property I wanted to draw your attention to was the auto embed method. And you can see if you hover on that, you get a pop-up here with a lot of information on how you can set the auto embedding up to run. I'll leave you to read those details later on, but for now, I'm just going to draw your attention across to the drop-down box for that, where we can see the different options here. None is the default. If we select none, we can come in and we can write our own values into the K history, the auto embedding dimension, and K tau, the embedding dimension, and K tau, the embedding delay. Having already selected a data file, we can now come and we can generate the code and compute. And we see a result here that looks consistent with 0, but more importantly over here in the code, we see we've set the properties for K and K tau here. Coming back, we can try other values for the auto embed method option. There are 5 here. For the moment, we're just going to look at the dest only options on RugViz and MaxCore AIS. We'll look at the other 2 options later in our short video. For these, what's important, we'll just select MaxCore AIS, and I'm going to set our manual ones back to 1. You don't have to do this. I'm just doing it so we don't cause confusion on the video here. What's important, when you select these auto embedding options, you need to set the search max for K and for tau, so it knows what the limitations are on where to search to. And for the RugViz criteria, you can change the number of nearest neighbors used there as well if you like. Okay, so as I said, looking at the auto analyzer, we've looked at the dest only options. There are other options we'll look at on the source embedding later on. So let's try an example using the MaxCore AIS dest only. We're going to scan the history length up to 10 and just leave our embedding delay at 1 for the moment. Let's have a quick look at that. Okay, so we've come in, we've set our auto embed method to MaxCore AIS dest only. We'll set our maximum embedding dimension for the search to 10. Now let's generate the code and compute. We see here now a result that is starting to look like it's potentially more significant, but most importantly for us at the moment, in the code now we can see the auto embed method being set. We can see the K-search max being set. And not only do we have our result, but if we just scroll up here in the properties, we can see what was found as the optimal K history, which was a history of 2 here. So remember that was set to 1 manually before. We let it search up to 10 and it found that 2 was the optimal history length using the MaxCore AIS dest only embedding. Okay, so as I just showed you on the GUI there, not only do we get the result, we can see the optimal parameters returned to us in the GUI. If you want to get them in code, you can do that via a get property call, which you can read more about in the Java docs. Okay, the next step in using our transfer entropy in practice is to set the source embedding. Now I've got to confess I gave you a simpler transfer entropy definition earlier. A more general definition includes a source embedding. That means looking at an embedded state of the source as well as an embedded state of the target. And that's what I'm showing in the equation here, that we could have an embedding dimension of L on our source Y and an embedding delay on that as well. So the big question is, when should we use a source state directly instead of a scalar for the source? There are a couple of possibilities here. One is if our observations, if our time series observations are masking some hidden Markov process, then it can be useful to use an embedded state to properly represent the underlying state of that process. For example, if we have brain imaging measurements, there what we have is a single dimensional observation on a multi-dimensional hidden Markov process. So that can be quite useful to model that more accurately using an embedded vector. We could also do this if multiple past states of Y are causal to X and we want to capture that in our model of the information processing here. Otherwise, we can build a set of contributors from the source via a non-uniform embedding, similar to the non-uniform embeddings we talked about for embedding the history of our target value. And we'll talk more about that in our next lecture. Looking at how to do that in the Auto Analyzer GUI, what we can do is go back to the KSG estimator, which I will at the moment, and look at the other options for the auto embed method. Okay, and here we see, if I pull down this drop-down menu again, there are 2 other options, RugViz and MaxCore AIS, that I didn't go through before. What they're doing is almost the same as what their counterparts dest only are doing, but they're embedding both the destination and the source up to the search maximum parameters that we looked at earlier. Importantly, note that selecting to embed the source will embed it independently of the target. The toolkit selects the source embedding to properly capture the source's own embedded state, or in other words, to maximize its own self-predictive information, not the information it provides about the target. To select the source embedding to maximize information about the target, you would want to follow the non-uniform approach that we'll discuss in the next session. Okay, so that's the difference between the dest-only options of those auto-embedding approaches and the options that embed the sources as well. Okay, and we just must remember that there's a slight change in the options here. We have 5 options now instead of just 3 compared to the active information storage, because we have this additional question of whether we're embedding just the target or the target and the source. Okay, the final parameter we can think about is having a source target delay. Now again, I still gave you a simpler transfer entropy definition earlier. A more general definition still includes a source target delay U, which we're signifying on the time index of our source variable y. So we're looking here at a transfer across U time steps from y to the next value of x. Everything we've looked at before, and even all our diagrams, we're just using the default source target time delay of 1. The advice on setting U is to set it to maximize the transfer entropy. Setting in that way has been proven to match the actual causal delay under simple conditions. As I said before, that's something, even though we're not expecting the information transfer to directly reflect causality, we do want our model of the information processing from the sources to the targets to include the causal contributors to that target, so we can measure, so we can model the information processing in a more meaningful way. That delay parameter can be set on the GUI very simply as well, using the delay property, and that's available on all of our estimators except for the kernel estimator. In the final short videos of this session, I'm going to give you a brief overview of our activity with cellular automata, and then we're going to look at some of the higher order or multivariate approaches to looking at conditional transfer entropy when we start to think about multiple sources to the target.